Let's give a round of applause to Al.
Oh, I got it. Okay, can anybody hear me? Am I coming on through the speakers? Perfect. Hey everyone, I'm Al, so I have a lot of links and some code on these slides. You can either do the thing where you take a photo of it with your phone, or you can check out this link, bit.ly/IndyPython 2018 Recursion. I first gave this talk at North Bay Python last year, and now I'm giving this talk again here. And so this is sort of a beginner's guide to recursion. It is, my talk is titled Recursion for Beginners, a beginner's guide to recursion. Actually, this is my talk, Recursion for Beginners, a beginner's guide to recursion, if you want to get technical about it. So anyway, yeah, I'm mostly known for writing this book. And I've spent several years now sort of teaching programming to beginners and trying to break down really complicated topics. And recursion is one of those things where a lot of people think of it as this like advanced, really intimidating, technical sorcery thing. And I thought, well, okay, there's got to be a way to like break this down into something that's really easy to understand. Because a lot of people think of recursion as recursion is hard or recursion is confusing. At least that's what I see whenever I try looking it up on Google. Yeah, I really like the fifth one on this list. Recursion is bad. Yeah, so I started looking into this and trying to figure out what exactly are the parts that people have difficulty with recursion. And before I get into that, though, there is something we just have to get it out there. It's just a big elephant in the room. So I'm just gonna say it. Go through all of the recursion jokes. Okay, just bear with me. To understand recursion, you must first understand recursion. Ha ha ha, it gets funnier every time I hear it. There's a whole bunch of these, let's just go through them all. The dictionary definition of recursion, which always ends with, see also recursion. If you Google the word recursion, the Google search results have a link back to the Google search results for recursion. I like my coffee like I like my coffee, recursive. I'm so meta, even this acronym is meta. That's really clever. And then there is the mythical creature, the recursive centaur, which is half horse, half recursive centaur. So when we look at all these jokes, we kind of get an idea of like, what exactly is recursion? And looking at these jokes, we see, oh, it's sort of like a meta, self-referencing, dreams within dreams kind of a thing. Here's a really basic, simple definition. A recursive thing is something whose definition includes itself. For example, here's a fractal, which is a recursive shape called Sierpinski's triangle. And in order to draw Sierpinski's triangle, this is done with Python's turtle module, by the way, which is part of the standard library. You don't have to install anything to get this nice fancy drawing stuff right here, and the code is at this link. To draw Sierpinski's triangle, you start off by drawing an equilateral triangle, and then you draw an upside down equilateral triangle inside of it, kind of making like the Triforce from Zelda. And then that'll give you 3 new triangles, and then you just draw Sierpinski's triangles inside of those triangles, which then gives you 9 triangles, and then you continue there, and then you have 27 triangles. So to draw Sierpinski's triangle, you have to draw Sierpinski's triangle. It's a recursive thing that its definition includes itself. Programming-wise, though, it's a lot simpler. In programming, recursion is just when you have a function that calls itself. Here's the shortest possible recursive function you can write. It's a function named shortest, and all it does is call itself, which is like a weird thing. You wouldn't think that this works. And in fact, it doesn't work. If you actually try to run this, you get this error, recursion error, maximum recursion depth exceeded. This is also called a stack overflow. Hey, just like that website. So a stack overflow is a kind of error that you can get when you are writing recursive functions. And really, before I go into recursion itself, I want to explain what stacks and specifically what the thing called a call stack is. This is where I think a lot of recursion tutorials go wrong, because almost all of the recursion tutorials I've seen never explain what the call stack is. So, yeah, going back to this joke, this is actually completely wrong. If you want to understand recursion, you should first understand stacks. So a stack it's one of the simplest data structures in computer science. It's just a data structure that holds a sequence of data and only lets you interact with the topmost item. You can add things to the top and take things off of the top. If you think of like a deck of cards, you can put down the 5 of diamonds, and then you put down the 3 of spades on top of that, and then put down the ace of hearts. And then you can take things off of the top of the stack. You can't mess with anything that isn't at the very top. We call this a philo data structure because the first card you put in will be the last card you take out. So just keep that in mind. Because Python already has a stack data structure. It's, oh, wait, right. So it's also like a meandering conversation. If you've ever had, or a technical talk that I should have prepared better for. If I'm telling you a story about my friend Alice, and then that reminds me of this story about Bob, and then I told you about Bob, and then that reminds me of a story about Carol, so I start talking about Carol, and then I finish that story about Carol, and then I go back and finish my story about Bob, and then I go back and I finish my story about Alice. That's sort of like a stack-like structure of that conversation. There's 2 main operations that you do with stacks. You can put things onto the top of the stack, which is called pushing an item onto the stack. And then you can take things off of the top of the stack, which is called popping. And then sort of a third operation is just telling if the stack is completely empty or not. Python already has a stack. It's the list. If you just restrict yourself to calling append and pop, then you can use a Python list as a stack. So here's an example of that. We have a list stored in spam. We can push the string Alice to onto it. Then we push Bob. Then we push Carol. Then we can pop Carol off of it. And when we look at the stack, you can see it has Alice and Bob. In this case, the top of the stack is the rightmost side of it. We can only add or remove things from the end. So there is, in particular, there is a stack called the call stack. And it keeps track of where the code execution is when you start calling functions. So this is some really basic code. It's just a function A that calls a function B, which calls a function C. And we have some print calls that say, oh, I'm starting up and then I'm ending. And when you run this by calling A, the output will be start of A, start of B, start of C, and then it goes in reverse order when it starts returning from those function calls, the end of C, end of B, end of A. So you probably already know this, but it really helps to say it explicitly out loud. Calling functions is not a one-way trip for the program execution. It's every time you call a function, Python remembers where that function call was so that when the function call returns, it will go back to that function. If you've ever heard the term goto considered harmful, this is from 50 years ago, back before programming languages really even had function calls, and you would just have a goto statement that would move the program execution to some other part of your code. And that was actually really terrible because it's hard to debug. If you had a program, you wouldn't be able to tell how the execution got to where it was. You just had all these go-tos sprinkled around and forming spaghetti code, essentially. So the call stack is how Python keeps track of where it should return to after each function call. So you can think of the call stack, it's just a stack data structure, and every time a function is called, Python will create a frame object and push it to the top of the stack. And every time a function call returns, it will pop it off of the stack. The frame object basically, this is an oversimplification, but it keeps track of where Python should return to when that function returns. So if you call A, and then you call B, and then you call C, and then C returns, then you start popping things off of the stack, and then you can pop B off the stack when B returns, and then pop A off the stack when A returns, just like that Alice, Bob, Carol conversation. So, right, recursion is a lot easier to understand if you understand stacks and the call stack, which is why it's terrible that most recursion tutorials don't explicitly mention all of this. You know, you sort of know like, oh, right, function calls return. Okay, I kind of get that, but it really should be made more explicit. It's also kind of hard to reason about with if it's not explicitly said, because the call stack isn't anywhere in your code. You can't point to a line of code in your program and say, oh, this is where the call stack is. It's handled by Python automatically in the background. But once you keep that in mind, okay, there's this thing called the call stack, frame objects get pushed onto it and popped off of it. It's going to make recursion a lot easier to understand. In fact, so I said it's invisible. Python has some introspective features with the inspect and traceback modules if you want to actually examine the call stack while your program is running. Doug Hellman has a great set of articles about these modules on his Python Module of the Week blog. So, okay, now that we know what call stacks are and what stacks are, we can now start talking about recursion. And the first thing that you need to know about recursion is that recursion is overrated. So a lot of people think of, I mean, it's still an important thing. It's a very useful and necessary thing to learn about. But a lot of people think of recursion as this magical, mysterious, all-powerful technique, when really it's not that great. In fact, sometimes it's completely inappropriate as a tool to use. A lot of recursion tutorials will go over factorial and Fibonacci, and it turns out these are actually great examples of what you don't want to use recursion for. So let's get started with factorial. This is a really simple math concept. Factorial is written with an exclamation mark. 5 factorial is just 5 times 4 times 3 times 2 times 1. 2 factorial is just 2 times 1. 4 factorial is 4 times 3 times 2 times 1. You can kind of get the idea about it. If we think about it, factorial has a recursive nature because 5 factorial is just 5 times 4 factorial. You can generalize, I mean, if you do the math, this actually works out well. And if you generalize it, the factorial of any number is just that number times the factorial of that number minus 1. So you can see that exclamation mark is on the left and right side of the equal sign. Like, it is a recursive thing. Its definition includes itself. So this seems like, okay, that's pretty easy. We can write Python code that can do this, right? We have a factorial function. It takes a number, and it just returns number times factorial number minus 1. It's a function that calls itself. That's pretty neat. We can calculate factorial 5. Except this doesn't work either. Here we go. We get that recursion error again. So this is that stack overflow. And we really need to dive into what causes stack overflows. Because if we go back to our original problem, in fact, 5 factorial is 120, and we're just multiplying it all the way down to 1. But that's not what our code technically does. When we run it, it's going to multiply it by 0, and then go on to -1 times -2, and so on forever. Well, actually, not forever, because remember, every time we call a function, we're creating a frame object, which takes up a little bit of memory, and then we put that onto the call stack. Whereas like an infinite loop, that's, you know, as long as your computer has electricity, your computer will just get stuck in that infinite loop forever. Whereas this is eating up more and more memory over time, and so eventually it's going to use up all of your computer's memory. Python is actually going to stop it before then, because Python will just say, hey, I have a set limit of 1,000 function calls. If you make 1,000 function calls without ever returning, I'm just going to raise this recursion error, because something has got to be wrong with this. So a stack overflow is basically when your recursive function just gets out of control and doesn't stop recursing. So we need something that tells our code our function to stop making further recursive function calls. Here you can see in the highlighted red part, Python has that 1,000 function call limit. That's sort of an artificial limit. You can actually change this, but not by that much. I think like on Windows, I got it up to like 2,500 before Python exe actually itself crashes. It doesn't even raise an error message. It just like completely falls apart. But for most purposes, 1,000 function calls is really all you need. So we need to make our recursive function stop calling itself in every possible case. And here's a hint. 1 factorial is just 1. It's just defined as that. So if we add some code that checks at the very start, hey, if number is 1, just return 1, then we're not going to make more recursive function calls. It's just going to return 1. So we call this the base case, and then we call the other part the recursive case. Every single recursive function that you write has to have at least 1 base case and 1 recursive case. The base case is the part of your recursive function that doesn't make another recursive function call, and the recursive case is the part that does. So if you don't have a base case, then your code is going to constantly do recursive function calls and never going to stop, and that'll cause a stack overflow. If you don't have at least 1 recursive case, then your recursive function isn't really a recursive function because it's not calling itself. Right, so that kind of explains it, but then, you know, people still look at this code and they're like, well, where does the 5 times 4 times 3 times 2 times 1 happen? This is a really confusing part about recursion and the factorial example in particular, it helps to try to remember the call stack is at work right here. Normally, the call stack, you have all these frame objects representing the different functions that are called, but in a recursive function, the function is calling itself. So all the frame objects are just for that same function. Otherwise, it's working the exact same as it is. Let's think about that stack of cards. You can only see the topmost card, but all those other cards are still down there underneath, the 5 of diamonds and the 3 of spades. It's all still there. So here's a diagram that shows you what's going on when we're trying to calculate the factorial of 5. Where it starts up here in the upper left and just goes to the right. We call the factorial function. We pass it 5. So that's creating a frame object, and we put it on the stack. And this the code in this function call says, I need to return 5 times factorial 4, which means we're calling a function. So we create a new frame object, and we stick it on top of the call stack. Notice that the frame objects are also where the local variables are stored. And right here, notice that we have multiple local variables named number that exist at the same time. That number equals 5 is still there right here. It's just underneath it. We can only see the topmost one. So now we call factorial 3, we add another card to the stack. Factorial 2, we add another card to the stack. We call factorial 1, and then that's our base case. We don't have to make more recursive function calls at that point. We know, like, oh, it's just 1, we just return 1. And so we start popping cards off of the stack here. So we start removing those frame objects. And when we take off that number equals 1 card, we're going back to the card that says number equals 2. Except now we know the full information to return this value 2 times 1. So then we can pop that off of the call stack. And then we're revealing this card again, where number equals 3. And then we can just return 3 times 2. And then we return 4 times 6. And we finally return 5 times 24, which is 120, which is what 5 factorial is. Remember, we have multiple local variables named number here. It's not just one global variable that we're overwriting and then it magically comes back into existence. There's actually, at 1.5 different variables named number. I think, so one of the reasons why factorial is a terrible example to use for recursion is because it's also really confusing because of this line, where half of this one line gets gets executed before all those recursive function calls take place, and then the other half takes place after all of those recursive function calls are done returning. So that number minus 1 part in blue, that's done before the recursive function call. Then we call factorial again, which calls factorial, which calls factorial, which calls factorial, and then that returns, and that returns, and that returns. And then we do the rest of that one line, return number times the return value from that factorial call. So this is, factorial, yeah, it's kind of a simple math concept, but as code, it's really awful. You can sort of think of it like this. What if I just hard-coded all of these different functions? I had like a factorial 5 function, and that just returns 5 times factorial 4, and I just had a different function for all of these. Now you can see, like, oh, this is where 5 times 4 times 3 times 2 times 1, I can see that in the code now. It makes it a little bit more obvious. The recursive factorial function is exactly this, except there's just one function. And we have those local number variables that contain the 1, 2, 3, 4, and 5. Now, if this is still confusing for you, that's okay. You can just do the iterative algorithm instead, which doesn't use recursion. It's just a loop. This is sort of, if somebody asks you to solve this problem, you'd probably write code that looks like this. And it's fine. It's perfect. You don't need to do recursion. This is totally adequate. It will probably actually be a little bit faster, maybe. Yeah, I forget the slide that comes up after this. Oh, right. OK, so I've shown you the recursive algorithm for calculating factorials, and I've shown you the iterative algorithm for calculating factorials. And now I'm going to show you a monstrosity, and that is an iterative algorithm that emulates the recursive algorithm. This will actually calculate the factorial of 5. It is a complete monstrosity of code. Never actually write code that like this. But really, there's nothing magical about recursion. Anything that you can do with a recursive algorithm, you can do with a loop and a stack. And this kind of proves it. You can do this with any recursive algorithm. I don't really have time to explain all of this code, but suffice it to say, I have created my own call stack using a Python list at the very top. And then I add my own frame objects, which are just dictionaries in my case. And whenever I want to simulate calling the function, I push one of these dictionaries onto the call stack, and then I pop it off of it. I'm not actually using Python's real call stack, because you can see there's no actual functions in here. It's just this weird while loop and all of this mess of code. But if you run this, it's going to print out 120, which is what 5 factorial is. But there is nothing special or magical or more powerful about recursive code. So anyway, right, so if recursion isn't more powerful and if it's not more elegant necessarily, when should we use recursion? And I thought about this a lot, and I came up with an answer. And then I thought about it some more, and I came up with a better answer. And recursion maps really well to your solution when there are 2 things true about your problem, when it has a tree-like structure and it also requires backtracking. You really need kind of both of these. It's mostly the backtracking. Whenever you have something that has backtracking, it's going to have like a tree-like structure involved. So trees are used all the time in computer science. It's just when you have like a node and it makes references to other nodes. And then those nodes can make references to other nodes, and so on and so on and so on. If you think about it, a list is really just a tree, except it just branches off to one node down the line. There's a lot of different things that use trees. You can think of a maze-solving algorithm. You can use recursion to solve this, because a maze is really just a giant compacted tree. You can follow nodes until you reach some sort of dead end, and then you can backtrack to an earlier node and then try to find a different path that way. Your file system is also a tree-like structure, because you have folders that can contain other folders. Has a recursive nature right there. Yeah, so if you don't have a problem that has a tree-like structure and requires backtracking, you really don't need to use recursion. You can use recursion. Technically, I showed you the iterative solution that does all the work of a recursive algorithm. You can use a loop and a stack to do any recursive thing. Technically, you can do the opposite too. You can take any loop in your code and then turn that into a recursive solution that just has a call stack on the side. That would be really over-engineered. Don't ever actually do that. Although I have seen people in the real world just like, I can use recursion to solve this. Yeah, please don't. And sometimes it's the completely wrong solution. It like objectively is bad. What happens when we try to calculate the factorial of 1001? Remember, Python has a built-in artificial limit of 1000 function calls. And if you call this, you're going to get that stack overflow error again. And that's because it's made 1000 function calls in a row without ever returning. And in this case, we could just try like upping that limit a bit, but it's sort of like if you have like a lot of credit card debt and you just want to raise your credit card limit, that will help maybe, but it's kind of also just putting off the problem. So there is a solution to this, and it's called tail call optimization, also called tail call elimination. And this is when your problem really is big enough where it will require more than 1000 function calls. The way you do tail call optimization is that you make the recursive function call the very last thing that happens in your function. So the recursive function call comes at the tail of your function. And the reason that this can prevent stack overflows is that if it's the very last thing your function does before returning, there's not going to be any code afterwards that needs to use local variables or anything like that. So there's no reason to create a new frame object for the next recursive function call. And if you don't have to do that, then the call stack never grows in size, which means that it's impossible for the call stack to grow too big and call a stack overflow. So the gist of it is tail call optimization prevents stack overflows. Kind of. It's also, tail call optimization is also overrated. For one thing, in order to do this, like our recursive factorial function is not tail call optimized because it has this part after the recursive function is called. So you have to rearrange your code do tail call optimization, and it becomes really ugly. Like we have this new accumulator parameter, and it's really weird, and our base case gets all messed up. But technically, yes, this can be tail call optimized. But the compiler or the interpreter has to be able to analyze your source code, realize, oh, okay, the last thing your recursive function does is call the recursive function. Now I can do this tail call optimization stuff. So really, tail call optimization is a compiler trick. But here's the thing, CPython doesn't implement it. The CPython is the Python interpreter that you download from python.org. But not only does it not implement it, it never will. Guido has this quote, and if you want a short answer, it's simply unpythonic. He goes into length about his reasoning in these 2 blog posts. But essentially, if you have to make tail call optimizations to your code, you're sort of mangling your code and you're making it less readable. And remember, it's more important in most cases for code to be understandable by humans rather than more efficient for computers to run. So that's factorial. It's the really common introductory problem that you'll face if you read recursion tutorials. The other one is the Fibonacci sequence. How many have been asked, like in coding interviews or in school or something, to calculate Fibonacci numbers? And it's so often people are like, oh, Fibonacci, you have to calculate this. It's another simple math thing. The Fibonacci sequence is, it starts off with 1 and 1, or sometimes 0 and 1 are the first 2 numbers. And the next number in the sequence is just the sum of the 2 previous numbers. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on forever. So you can calculate the first Fibonacci number or the second Fibonacci number. Those are easy, they're both just 1. Or the third Fibonacci number after that. You can generalize this where if you want to calculate the nth Fibonacci number, then you need to calculate the nth minus 1 and the nth minus 2 Fibonacci numbers. So it has a recursive nature. It's the definition of the Fibonacci number includes the Fibonacci numbers. The base case in this case is 1 and 2. The first and second Fibonacci numbers are just 1, so that's your base case right there. Right, so we can start, this seems pretty straightforward. We have our base case, we have a recursive case. If you're ever writing recursive code, that's a good way to just get started, is ask yourself, what's my base case, what's my recursive case? Should I be using recursion to solve this problem? And if you calculate the 10th Fibonacci number, this function will tell you it. And if you calculate the 35th Fibonacci number, it will tell you the 35th Fibonacci number after 8 or 10 seconds. And then if you ask it to calculate the 100th Fibonacci number, it will take several centuries to answer that. And the reason is because this part here in red, every call you make to the Fibonacci function results in 2 more calls to the Fibonacci function. It's like a hydra. Every head you cut off, 2 more heads grow in its place. So we end up having a lot of work that needs to be done. So here I'm drawing a tree structure here where we're calculating the 6th Fibonacci number, which involves calculating the 5th and 4th Fibonacci numbers, and then that just spreads out there. It ends up being a lot of work. Not only that, but it also ends up being a lot of repeated work. The 4th Fibonacci number isn't going to change. It's the 4th Fibonacci number. But here we call fib of 4 twice, and then we calculate the 3rd Fibonacci number 3 times. The way that we can sort of fix this is if we just create a cache, and the first time we calculate a Fibonacci number, we'll just remember it. So we're using up memory to speed up our algorithm. And then we can prune away a lot of the branches just by remembering, oh, if I ever see Fibonacci 3, I can know that's 2. And if I ever see Fibonacci 4, I know that's 3. And we can save a lot of time doing that. This is called memoization. And your phone's autocorrect will always want to correct this to memorization. It's memoization without the R. When I first learned about this, I just thought my CS professor had mispronounced it or something like that. But yeah, basically we just create a cache. In this case, it's just a dictionary. And the first thing that happens in our function is it checks the cache. And if we've already calculated this before, we can return that value. We don't have to run the rest of the code in this function. Otherwise, we just continue as normal, except before we return the result, we're going to remember that result by storing it in the cache. Python is actually pretty good because this is a fairly common thing that you want to do. Python has this all built into a decorator called LRU cache inside of the functools module. So you can just add this one line of code and it basically does that for you. But again, like memoization, just like tail call optimization, it's sort of a solution to a problem we wouldn't even have if we just did the iterative approach instead of the recursive approach. It's sort of this weird Band-Aid solution. But there are times when a recursive approach or a recursive solution is going to be really great when you have tree-like structures or backtracking. So it's really good to know about memoization. Tail call optimization you can totally forget about in Python because Python doesn't do it. Memoization is pretty handy. LRU stands for least recently used, last recently used, least recently? Yes. It's a really common caching algorithm in computer science. So anyway, wow, I'm running out of time. So perfect. Here's a quick overview. Remember, you can just download these slides later. To understand recursion, you must first understand stacks. Don't let anybody try to tell you that silly little joke because it's not true. Recursion is often really hard to learn because the call stack is invisible. It's nowhere inside of your code. You can't see it anywhere. But when you are writing recursive functions, remember, you're always going to need at least one base case. Otherwise, your code's not going to stop calling itself, and it will cause a stack overflow. And it needs one recursive case to be a recursive function. Function calls push a frame object onto the call stack, and returning from a function call pops it off. Stack overflows happen whenever you make too many function calls in a row without returning. And remember, anything you can do in recursion, you can do with a loop and a stack. And you should only use recursion really when your problem has a tree-like structure and requires backtracking. Otherwise, you really don't need to use recursion. You still can, it's just not really advised. Tail call elimination prevents stack overflows. It does that by preventing the call stack from growing, but you have to really mangle your code to get that to work, and CPython doesn't do it anyway. And memoization can speed up your recursive algorithms by just using a cache for all the return values. That's everything here. Wow, 31 minutes, perfect. If you need to talk to me about this, then you can contact me here, or I'll be around for the rest of the night. Thank you very much. Oh, yeah, I guess we have like time for a couple of questions.
Yeah. I'd love to see if the community has some questions for you.
And remember, it's really great if you keep your question in the form of a question.
If you're stuck,
Oh, well, I have this mic. Yeah.
if you're stuck on problems where you have to use the tail call optimization, what is an alternative?
Oh, for tail
Or
call
are you just
optimization?
stuck
You're pretty much stuck. You're pretty much forced to have your recursive function cause stack overflows. You can do what I did with that monstrosity code and just create your own stack using a Python list, essentially. But at that point, you're really no longer even using recursion. You're using an iterative approach with a loop and a stack.
Okay.
Oh, yeah.
Yeah, I remember people mentioning this, like that you couldn't do this on the JVM because it locks the stack for security. But in addition to the tail call optimization, they talked about a springboard. Do you know what a springboard is?
Springboard. I have no idea.
It's another way of dealing with deep.
Should make a note. Springboard. Yeah, sure. Next.
Okay. Early on, you griped about factorial being an awkward function to introduce recursion with, because that code that ran before recursion and code that ran after recursion.
Yeah.
Do you have a suggestion of a function that's less awkward, or is that a blind spot of yours as well?
Oh, man. This is a really good question, and I should come up with an answer to give to people. I mean, I just sort of go over factorial and Fibonacci anyway, just with these caveats. I don't know. Let's. So I have this one page where on my GitHub account. Oh wait, I'm not even connected to the Wi-Fi. I had that one GitHub link that had a whole bunch of random recursion examples. But like, Towers of Hanoi, that's a common one, but that's sort of complicated. I don't know, maybe like if you want to give somebody an assignment, having something that can search through the folders on their hard drive just by like, start at this folder and then examine all the subfolders in that folder. And then you can just recall that same function because you can look at that subfolder and examine all the subfolders in that subfolder and so on and so on. That might be a less awkward way. I think a lot of computer scientists, because computer science kind of grew out of mathematics, they really like latch on to like factorial and Fibonacci. Like if you've ever seen that website Project Euler that has all those programming problems, there's a lot of like mathy things on there. And computer science and programming is not necessarily just mathematics, unless you ask a CS professor. Yeah, next question.
I was going to say there are a bunch of tail call optimization decorators. Most of them are kind of taking the approach of rolling your own stack or a function called heap memory. You can still run out of memory with them, but at least you don't hit the limit on the stack.
Yeah. Is this in the Python standard library?
No, none of these.
Oh, okay,
absolutely
yeah.
not. Yeah, but if you like Google tail call optimization Python decorator, you'll find like a million Stack Overflow, Reddit, But I was going to ask, so it seems like the interest in this is mostly like from the theoretical computer science, everybody should understand recursion perspective. Do you see people using recursion in Python code? Is there any use in the wild ever of like change the stack limit?
I mean, sure. I've never seen recursion actually used. Like when I was working as a software developer, no, recursion never comes up. I mean, you'll find recursion in coding interviews much more than you will find it in coding jobs. Everybody, if you're doing an interview and you just like, I don't know, what can we ask them? Let's try recursion or like all these other things from freshman year of computer science because we think that qualifies you as a software engineer for some reason. Using the flood fill. Oh, the flood fill algorithm. That's a really great algorithm. If you've ever used like MS Paint, here, I'll just punch it up real quick. This was something like if you just draw a weird shape in here and then you get that paint bucket tool and you can click inside of it and it'll fill any arbitrary shape. This is actually commonly done with recursion. Actually, I don't think so because it's really easy to cause a stack overflow unless you have tail call optimization, so I wouldn't use it for that. But this is kind of a fun thing. Really what this algorithm is doing, and this blew my mind when I first discovered it, is that point that you click on, it says like, oh, okay, so this is a white pixel. I will look at the neighboring pixels to see if they were white pixels, and if they are, then I'll color those and then check their neighbors, and I'll check the neighbors of those neighbors, and then check the neighbors of those neighbors. And the end effect is that you can fill in this like in any arbitrary shape. So this is kind of fun. It's also graphical. This would probably be a really good thing to do with recursion. I have on the GitHub links, I think I have an example where instead of like graphics, I just have a field of ASCII characters, and you can sort of fill it in that way. Yeah, so personally, I think flood fill was the only time I used recursion, and then even then I got rid of it and used an iterative approach anyway. Technically, you don't even need a stack. You can use any data structure because you don't really need the backtracking. You don't have to do in a specific order. You can do it really in any order. But yeah, I don't actually use recursion that often in real world programming.
To see examples, look at dynamic programming, longest common subsequence. There's a top-down and bottom-up. The top-down uses the LRU, least recently used cache.
Yes. So dynamic programming, which I love the story of because it sounds like this, like, ooh, dynamic programming. It's really great. It actually came because I believe this was during World War II, somebody correct me if I'm wrong, but a computer science researcher wanted to have funding from the military to do computer science research, but the general who was in charge of it didn't really like research, wanted something more practical. So it's not research, it's dynamic programming, and that's where it got its name from. Really, dynamic programming is, I guess this is probably a bad definition of it, but they're a set of problems where the naive, straightforward approach is actually kind of terrible, and if you do a little bit of setup work beforehand, then you can use that information to solve the problem. But a lot of dynamic programming uses recursion, and functional programming languages make heavy use of recursion. So yeah, that's one example of where recursion would be used. So I know in real world terms like Levenshtein distance, which is basically, or the editing distance. If you want to turn the word cat into the word rat, then you just do like one substitution. Or if you want to turn the string cat into the word rate, then you do one substitution with CAT to RAT, and then you do one addition of adding the E at the end. So the Levenshtein distance is, I'm not even sure if I'm pronouncing that correctly, but the edit distance of cat to rate would be 2. in that case. And that's a dynamic programming problem, and it also uses recursion in that. Although technically you don't have to use recursion in it. You could just create your own stack and loop. Yeah, any other questions?
All right.
All right.
Thank
Okay.
you, Al.
Thank you very much.